All right, today we're tackling a really fascinating dilemma, one that literally almost every Haskell developer bumps into at some point in their journey. It's kind of the ultimate architectural showdown, strict versus lazy text representation. In this explainer, we're going to look at the real-world performance impacts of these two choices, and, more importantly, why picking the wrong one might just be quietly dragging down your entire system.
Section 1. The Lazy Text Temptation.
Okay, let's dive right into this. So, during a recent code-based refactoring of a document generation program, it's called XS to ebook, the developer, Ang, decided to standardize their text type usage. They actually went ahead and stripped out all the strict text, unified the whole shebang to lazy text, and asked a perfectly relatable question. If the lazy text can handle large amounts of text efficiently, why not make this the default choice?
I mean, it's an incredibly tempting thought, isn't it? Why not make lazy text the universal default? If it's powerful and, efficient enough to chew through massive document conversions and heavy data streams, surely it can handle the smaller, everyday text tasks, right? Why even bother juggling two different modules when you can keep it simple and just use one type for everything? Well, today we're treating this as our central myth to bust. We're going to break down exactly why a one-size-fits-all approach to text in Haskell might actually be secretly sabotaging your app's performance.
Which brings us to Section 2. The hidden costs.
So the core mechanism behind lazy evaluation is something called a thunk. Basically, it's an evaluated later pointer. To put that into perspective, imagine handing someone a massive, heavy, locked briefcase that just contains an IOU to calculate a tiny three-letter word, instead of simply handing them a tiny slip of paper with the word already on it. Because of how laziness actually works under the hood, the memory overhead of that heavy briefcase, the thunk, can absolutely outsize the tiny text data it's supposed to represent.
And man, this leads to a whole cascade of downsides when you misuse lazy text on small pieces of data. First, as we just saw with our briefcase analogy, the memory overhead vastly exceeds the actual text size. It's just wasted space. Second, you run a massive risk of memory leaks. Because these thunks hold on to references until they're finally evaluated, data held in memory can become completely outdated but still trapped there, unable to be cleared away. And third, all of this creates an incredible, entirely unnecessary strain on your garbage collector. I mean, the GC has to work overtime managing and tracking all these complex, lingering pointers instead of just quickly sweeping up simple, direct values.
So, this brings us to a pretty stark reality for your daily coding life. Small data plus lazy text equals silent leaks. Think about the basic building blocks of your own applications for a second. Are you using lazy text to store a simple, tiny JSON key? What about a short configuration string or maybe a basic database identifier? Because if you're defaulting to lazy text for those kinds of tasks, you're literally handing out thousands of those heavy briefcases. You are silently bleeding memory and unnecessarily taxing your system's resources, all for tiny bits of data that really should have been evaluated instantly.
All right, moving on to Section 3, strict versus lazy rules. And this brilliantly illustrates exactly how you should divide up your workloads. Let's look at the breakdown. Strict text is highly efficient for the garbage collector when you're dealing with fixed, small to medium data. You really want to make this your absolute go-to for configuration values, JSON keys, database records, and identifiers. Basically, keep it strict, keep it lean. Conversely, lazy text is where laziness truly shines. You want to reserve that for handling large files, streaming massive amounts of data, or doing heavy document generation, just like Ang's X2 ebook converter. Right tool for the right job, essentially.
Which leaves us with one final, pretty urgent question for you to ponder as we wrap up this explainer. I want you to look at your own codebase right now. Are hidden thunks leaking memory in your small text data? It might seriously be time to do a quick audit of your text types and just make sure your simple JSON keys and identifiers aren't hiding inside heavy evaluated later pointers. Swap those back to strict text and give your garbage collector a much-needed break. Thanks so much for joining me for this explainer today, and happy optimizing.